What if we're not alone in the universe? Picture this: an invisible whisper cutting through the vast darkness of space, a radio signal so precise it defies explanation. Scientists first detected these cosmic anomalies decades ago, pulses of energy appearing and vanishing like interstellar Morse code. Some last mere milliseconds, others repeat in patterns that seem almost deliberate. Are they natural phenomena, or could they be attempts at communication from civilizations light years away? From the infamous WOW signal to fast radio bursts that baffle astronomers, these mysterious transmissions blur the line between science and speculation. Today, we're diving deep into the enigma of interstellar signals, exploring the cutting-edge technology hunting them, the theories trying to decode them, and the spine-tingling possibility that we might one day receive a message not meant for human ears. Whether it's pulsars playing tricks or something far more extraordinary, this journey through the cosmic static will change how you listen to the silence of space. So lean in, turn up the volume, and let's trace those whispers across the void together. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars. So why does it feel so eerily quiet? This is the heart of the Fermi paradox, a puzzle that haunts astronomers and dreamers alike. If life is common, where is everyone? Some theories suggest the answer lies in something called the Great Filter, an invisible barrier that prevents civilizations from advancing far enough to communicate across the stars. Maybe it's the rarity of life itself, or perhaps every advanced society hits a catastrophic wall: nuclear war, climate collapse, or even something we haven't yet imagined. Then there's the staggering challenge of interstellar communication. Even if another civilization is out there broadcasting, their signals might be too faint, too brief, or too alien for us to recognize. The whispers we've detected, those fleeting radio bursts and unexplained patterns, could be cosmic static, the distant echoes of dying stars, or they might be the first tantalizing clues that we're not listening closely enough. After all, space isn't just vast, it's also old. A signal sent thousands of years ago might only now be reaching us, long after the civilization that sent it has vanished. The silence could mean we're alone, or it could mean we're simply not hearing the conversation happening all around us. And that's what makes these mysterious signals so electrifying. They could be the key to solving the paradox, or another layer of the mystery altogether. Fast radio bursts are one of the universe's greatest enigmas, cosmic flashes, so powerful they release more energy in milliseconds than our sun does in 3 days, yet vanish before we can pinpoint their source. First discovered in 2007, these mysterious pulses arrive from galaxies billions of light years away, some appearing just once, while others repeat in erratic patterns that defy simple explanations. One leading theory suggests they originate from magnetars, highly magnetized neutron stars that occasionally unleash catastrophic starquakes, rippling spacetime with intense radio waves. Others propose collisions between neutron stars or exotic objects like cosmic strings could generate these fleeting bursts, but the most tantalizing possibility, that some FRBs might be artificial in nature, interstellar beacons, or even leaks from advanced alien technology. In 2020, astronomers detected a repeating burst from within our own Milky Way, tracing it back to a known magnetar, which bolstered the natural origin theory. Yet the mystery only deepened when another repeating FRB exhibited a strange, predictable cycle, flaring up every 157 days like clockwork, a rhythm that doesn't neatly fit known astrophysical processes. Could this be a natural cosmic pendulum, or something more intentional? The challenge lies in the signal's brevity; most last just thousandths of a second, leaving astronomers scrambling to study them before they fade into the void. New telescopes like Canada's CHIME array are now scanning skies around the clock, capturing hundreds of these bursts in hopes of finding patterns that might reveal their true nature. Whether they're stellar death throes or cosmic hellos, fast radio bursts remind us that the universe still holds mysteries we've only begun to unravel, each pulse a whisper in the dark begging to be understood. In 1974, humanity took its first deliberate shout into the cosmic void, the Arecibo message. Beamed from the massive radio telescope in Puerto Rico, this 3-minute transmission contained a binary-coded diagram of our DNA, the solar system, and even a stick figure of a human. It was more symbolic than practical, targeted at a star cluster 25,000 light-years away, ensuring no quick reply. But it marked a pivotal moment. We weren't just listening anymore, we were trying to converse. Decades later, the question lingers: has anyone responded? Enter the WOW signal, a 72-second burst of radio waves detected in 1977 that matched the exact frequency scientists predicted aliens might use. It came from the direction of the Sagittarius constellation, vanished as suddenly as it appeared, and was never heard again. Was it a cosmic coincidence or a fleeting hello? The challenge lies in deciphering intent. Natural phenomena like pulsars or quasar emissions can mimic artificial signals, while truly alien communication might be so advanced, it's indistinguishable from background noise to our primitive tools. Consider the case of HD 164595, a star system where researchers found a repeating signal in 2021 that seemed to align suspiciously with expectations of a deliberate transmission. Further study revealed it was likely interference from passing satellites, but the moment captured the existential roller coaster of the search: elation, followed by sobering skepticism. Even if we intercept a genuine message, would we recognize it? An advanced civilization might encode information in neutrino bursts, gravitational waves, or quantum particles, mediums we're only beginning to explore. And then there's timing. The sheer scale of cosmic distances means a dialogue could span millennia. Our first real conversation with another world might play out across generations, each reply separated by centuries of silence. Yet projects like METI, messaging extraterrestrial intelligence, continue broadcasting, crafting messages designed to transcend language and biology with universal mathematical and scientific concepts. It's a gamble. Some, like Stephen Hawking, warned against advertising our presence to potentially hostile neighbors, but the urge to reach out persists. After all, if we stop sending signals, we might never know if someone's been whispering back all along. The summer of 1977 gave us one of the most electrifying cosmic mysteries of all time: the WOW signal. It wasn't just another blip in the data. This was a signal so strikingly artificial that astronomer Jerry Amon famously circled it on the printout and scrawled, "Wow." In the margin, lasting 72 seconds, it blasted through the radio telescope at Ohio State University's Big Ear Observatory, matching the exact frequency scientists had predicted an extraterrestrial civilization might use: the hydrogen line at 1,420 megahertz. What made it extraordinary wasn't just its strength or frequency, but its behavior. Unlike natural cosmic noise, it was a narrowband signal, the kind produced by intentional transmitters, and it appeared to originate from a seemingly empty patch of space near the Sagittarius constellation. Yet, despite exhaustive searches, it never repeated, vanishing as mysteriously as it arrived. Decades later, debate still rages over what caused it. One camp argues it was a natural phenomenon, perhaps a comet's hydrogen cloud reflecting sunlight, except the signal's characteristics don't quite fit. Others suggest it might have been a military transmission or a rogue satellite, though no known human activity matched its profile. Then there's the tantalizing third possibility that it was a fleeting, one-time beacon from an advanced civilization, a cosmic greeting we caught by pure luck. The very brevity of the wow signal is what fuels the mystery. If it was artificial, why hasn't it been heard again? Was it meant for someone else, sweeping past Earth like a lighthouse beam in the dark? Or are we simply not listening in the right way, missing follow-up signals encoded in a format we don't yet understand? Modern SETI projects still hunt for echoes of the wow signal, using technology far more sensitive than big ears. Yet, if anything, its legacy has deepened the philosophical divide in the search for extraterrestrial intelligence. Some researchers argue we should focus on transient signals, brief, unpredictable bursts like wow, while others advocate for continuous monitoring of star systems, hoping to catch a deliberate, sustained transmission. Then there's the eerie thought: if a signal like wow was artificial, its one-time nature suggests a civilization might not bother repeating messages, assuming any listeners would be advanced enough to catch it once. That raises an even more profound question: how many signals like wow have we already missed, lost in the static of the universe before we even knew how to listen? The mystery endures, a ghostly whisper from the cosmos that refuses to be forgotten. And until we find another like it or finally decode its origin, the wow signal remains both a milestone and a riddle, proof that sometimes the universe speaks in riddles we're still learning to understand. For nearly 70 years, the search for extraterrestrial intelligence, or SETI, has turned Earth into one giant listening station, scanning the skies for whispers that don't belong to nature. It all started in 1959, when astronomers Giuseppe Cocconi and Philip Morrison proposed an audacious idea: that alien civilizations might use radio waves to communicate, just as we do. The following year, Frank Drake aimed the Green Bank telescope at two nearby stars, Tau Ceti and Epsilon Eridani, marking humanity's first deliberate search for cosmic neighbors. Today, SETI has evolved from a fringe idea to a sophisticated scientific endeavor, deploying arrays of radio telescopes that sift through the static of the universe like detectives, analyzing white noise for hidden messages. The strategy comes in two flavors: targeted searches and wide field surveys. The first focuses on promising star systems, especially those hosting exoplanets in habitable zones, while the second casts a net across vast swaths of sky, hoping to catch anomalies by sheer volume. But here's the catch: space is noisy. Earth's own radio chatter, satellite interference, and even cosmic phenomena like pulsars create false alarms that waste precious telescope time. That's why modern SETI relies on algorithms to flag only the most suspicious signals, those narrowband frequencies that nature struggles to produce, or pulses with unnatural regularity. Take Project Phoenix in the 1990s, which examined 800 nearby stars with military-grade precision, ruling out thousands of candidates before spotting a handful of unexplained blips, each later debunked as human-made interference. Then there's the scale problem. Imagine trying to hear a single conversation in a stadium where every attendee is shouting. That's SETI challenge when scanning the Milky Way's 200 billion stars. Breakthrough Listen, launched in 2016, aims to change that. Backed by billionaire Yuri Milner, it's the most comprehensive search yet, scanning 1 million stars and 100 galaxies across 10 billion radio channels. Already, it's cataloged dozens of intriguing signals, like the one from Proxima Centauri in 2020, a narrowband emission that matched no known satellite or aircraft. Hopes soared until researchers traced it to a malfunctioning computer on Earth. These near misses underscore the agony of the search. Every detection teeters between potential discovery and heartbreaking false alarm. But what if we finally find something? Decoding an alien message might be even harder than detecting it. Would it be a mathematical primer, a cosmic Rosetta Stone, or something beyond human comprehension? Some propose looking for repeating prime numbers, a universal signature of intelligence, while others suggest scanning for compressed data packets hidden in the signal's structure. The real shock might come if we intercept not a deliberate message, but leakage, the galactic equivalent of catching a neighbor's phone call. An advanced civilization's radar, broadcast TV, or even propulsion systems could leak signals we'd recognize as artificial. Yet SETI faces a paradox. The more we expand the search, the more we realize how little we've truly listened. Current efforts cover a fraction of possible frequencies, star systems, and signal types. New telescopes like the upcoming square-kilometer array promise to change that, scanning the sky with unprecedented sensitivity. But until then, every quiet night at a radio telescope holds the same electric question: will tonight be the night the silence finally breaks? The answer could come tomorrow, or it might take centuries, but as long as that uncertainty exists, the search will continue, one frequency at a time, chasing the faintest hope that somewhere in the void, someone else is listening too. Imagine picking up the phone and hearing a voice speaking in a language completely alien to anything on Earth. Now multiply that challenge by cosmic proportions. If we ever detect a signal from another civilization, decoding it could make translating ancient hieroglyphs look like child's play, the first hurdle. We'd have to confirm it's artificial at all. Natural space phenomena, colliding neutron stars, swirling plasma clouds, can produce eerily perfect radio bursts that mimic intelligent design. But let's say we're certain the signal pulses in prime numbers, repeats in clean mathematical intervals, or carries some other fingerprint of craftsmanship. Now the real work begins. Scientists have theorized for decades about what form an interstellar message might take. Many bet on mathematics as the universal language. After all, the laws of physics are the same everywhere in the cosmos. A sequence of prime numbers, the atomic structure of hydrogen, or even a simple counting pattern could serve as a cosmic handshake. The Arecibo message sent in 1974 used this approach, encoding information in binary pulses to depict human DNA and our solar system. But critics argue this assumes aliens think like we do. What if their math operates in dimensions we can't perceive, or their consciousness processes reality in a way that renders our concepts of numbers meaningless? Then there's the problem of symbolism. Humans communicate through shared context. A heart means love, a red light means stop, but an alien species might have no visual organs, no concept of color, or entirely different social instincts. Even something as universal as a circle could be misinterpreted. To a civilization living inside a Dyson sphere, it might signify home rather than a geometric shape. Some researchers propose using the periodic table as a Rosetta Stone, since elements like hydrogen and oxygen behave predictably across the universe. Others suggest embedding instructions within the signal itself, a sort of how to read this manual coded in fundamental constants, the real curveball. Time, an advanced civilization might compress vast amounts of data into a single burst, expecting recipients to unpack it over centuries, or they could transmit in a medium we're not even monitoring yet: neutrino beams, gravitational waves, or quantum entanglement. This raises a chilling thought. What if we've already received an alien message but lacked the tools to recognize it? The infamous WOW signal might have carried layers of information our 1970s tech couldn't decode, like finding a USB drive in the Middle Ages. And then there's the elephant in the room: intent. Not every detectable signal would be a friendly hello. It might be automated infrastructure chatter, a distress call from a long-dead civilization, or even a cosmic trap. The darker interpretations fuel debates about whether we should reply at all, a dilemma that splits the scientific community. Yet for every skeptic, there's an optimist pointing to those strange repeating signals from deep space, the ones that defy natural explanation. Each pulse could be a page in a galactic encyclopedia, waiting for the right species to piece it together. Until then, the silence isn't empty, it's a classroom, and we're just learning the alphabet. Among the hundreds of detected fast radio bursts, one stands out like a cosmic fingerprint: FRB 121102. Unlike fleeting bursts that vanish forever after milliseconds, this signal from a dwarf galaxy 3 billion light-years away has repeated sporadically since its discovery in 2012, defying every expectation of how these phenomena behave. Each pulse arrives with the energy of 500 million suns, yet the pattern feels almost playful, sometimes silent for months, then suddenly erupting in clusters of activity. The unpredictability alone makes it extraordinary, but what truly sets this signal apart is its home, a turbulent region of space near a massive black hole, where extreme forces twist magnetic fields into knots. At first, astronomers pinned the bursts on magnetars, supermagnetic neutron stars known to produce similar emissions, but as observations piled up, inconsistencies emerged. The signal's polarization, the way its waves twist as they travel, suggests it's passing through an intensely magnetized environment, far stronger than typical magnetar surroundings. Some researchers propose an exotic hybrid, a magnetar orbiting a black hole, its eruptions amplified by the hole's gravitational grip. Others wonder if we're seeing something entirely new, a cosmic lighthouse, perhaps, or even an engineered beacon. The latter isn't as far-fetched as it sounds. A civilization capable of harnessing black hole energy might use such bursts for interstellar communication, their immense power allowing signals to punch across the universe. Then there's the location itself, a tiny, metal-poor galaxy vastly different from our Milky Way. If FRB 121102 is natural, why haven't we found others like it in similar environments? The absence of comparable signals fuels speculation that this might be a one-of-a-kind event, or a one-of-a-kind object. Breakthrough Listen once trained its telescopes on the source for 5 hours straight, capturing 15 bursts in a single session. Yet even with this data, the signal's secrets remain locked. The bursts vary in brightness and spacing, with no decipherable pattern, almost as if they're avoiding predictability. Technology adds another layer of frustration. Our telescopes, though advanced, still struggle with radio frequency interference, human-made signals masquerading as cosmic phenomena. Worse, the vast distances dilute the bursts, leaving astronomers to piece together meaning from whispers buried in static. Future instruments like the Square Kilometre Array could change the game, offering the sensitivity to catch subtle details invisible today. Until then, FRB 121102 lingers as both a tantalizing clue and a stubborn riddle. Whether it's the scream of a dying star or the first page of an interstellar message, one thing's certain: this isn't just another burst. It's a conversation waiting to happen, if only we could learn the language. Our search for cosmic neighbors might be like trying to spot a candle flame from across an ocean with a pair of binoculars. Not impossible, but staggeringly difficult with the tools we have. Radio telescopes, our primary ears to the universe, face limitations that even their immense dishes can't overcome. Take the famous Arecibo telescope before its collapse. Though powerful enough to ping asteroids with radar, its listening range was a mere fraction of the Milky Way, like overhearing one conversation in a city of billions. The signals we can detect weaken with distance, diluted by the inverse square law until they blend into the cosmic background hum. Even if an alien civilization were broadcasting directly at Earth, their transmission would need to outshine our sun's natural radio emissions by a factor of thousands just to register as suspicious, a feat requiring energy levels we can't yet fathom. Then there's the sheer scale of the search. The Milky Way alone spans 100,000 light-years, and we've barely scanned a teaspoon of its stars for fleeting signals. Most SETI efforts focus on the water hole, a quiet band of frequencies between hydrogen and hydroxyl wavelengths where nature's noise is minimal. But what if aliens aren't using radio at all? Advanced civilizations might have moved beyond electromagnetic waves, communicating through neutrino beams that slice through planets unimpeded, or quantum-entangled particles allowing instant messaging across light years. These technologies, still in their infancy for us, could be routine for species millennia ahead. We're essentially listening for smoke signals in an age of fiber optics. Even time itself works against us. Human radio broadcasts have only leaked into space for about a century, a blink in cosmic terms. If another civilization's transmissions swept past Earth before Marconi invented the radio, or if their signals arrive millennia from now, we'd miss each other entirely. The universe isn't just vast, it's asynchronous. This timing problem extends to our own active searches. The famous Arecibo message, aimed at a star cluster 25,000 light-years away, won't reach its destination until long after the telescope itself has crumbled. Any reply would take twice as long, assuming anyone's still listening. Yet the most haunting limitation might be recognition. An alien signal could be right in front of us, encoded in a medium or structure we don't yet recognize. Imagine a library where every book is written in invisible ink, readable only under light we've yet to discover. This is why newer projects like Breakthrough Listen are expanding beyond radio, scanning for laser pulses and other technosignatures. Upcoming tools like the Square Kilometer Array could revolutionize the hunt, with sensitivity sharp enough to detect airport radar-level transmissions from dozens of light-years away. Until then, the silence isn't proof we're alone, just proof we're still learning how to listen. The cosmos loves playing tricks on us. What seems like an alien hello often turns out to be nature's elaborate prank. Take pulsars, for instance. These rapidly spinning neutron stars emit beams of radio waves so precise they were initially nicknamed LGM signals, short for Little Green Men, when first discovered in 1967. Their rhythmic pulses, arriving with clockwork regularity, mimic the kind of deliberate transmission an intelligent species might produce. Yet they're nothing more than celestial lighthouses, their precision born from the brutal physics of collapsed stars. Then there's the eerie chorus of magnetars, neutron stars with magnetic fields so intense they crack under the strain, releasing bursts of energy that can briefly outshine entire galaxies. These starquakes produce signals resembling artificial broadcasts, complete with patterns that tease the imagination before vanishing into the void, but not all cosmic static fits neatly into known categories. Some fast radio bursts defy explanation, their bizarre behaviors straddling the line between natural and engineered. Consider FRB 190520, a signal that arrived with a distinctive double peak, as if carrying encoded information, yet originating from a region of space with no obvious cosmic fireworks. While most astronomers lean toward astrophysical origins, a stubborn few point to its peculiar structure, wondering if it's too orderly to be purely natural. The debate mirrors early 20th century arguments over Martian canals, a collision between what we know and what we hope might be out there. This tension drives science forward, pushing researchers to devise ever more sensitive instruments to distinguish between nature's quirks and potential technosignatures. Amid the speculation, one ethical dilemma looms large. If we do intercept a signal that defies natural explanation, should we respond? The scientific community is split. Some, like the late Stephen Hawking, warned against announcing our presence to potentially hostile civilizations, drawing parallels to Earth's history of colonial encounters. Others argue that any species capable of interstellar communication would likely have moved beyond primal aggression, and that hiding denies humanity a chance to join a galactic dialogue. The very act of listening, then, becomes a philosophical tightrope. We yearn for connection yet fear the consequences of being heard. Perhaps the greatest irony is this: the more we uncover about the universe's natural wonders, the stranger and more wonderful the remaining anomalies become. Whether they're cosmic oddities or deliberate messages, these whispers across the void remind us that the universe is far richer, far stranger than we've yet imagined. And that duality, the push and pull between known and unknown, is what keeps us staring at the stars, ears tuned to the static, waiting for the next enigma to crackle through the dark. The moment we detect a signal that's unmistakably artificial, humanity faces a choice unlike any other. Do we answer? This isn't just a scientific decision. It's a moral crossroads that pits curiosity against caution, hope against fear. On one side, visionaries like Carl Sagan champion the idea that any civilization advanced enough for interstellar communication would have likely outgrown violence, their technology a testament to cooperation rather than conquest. Imagine the breakthroughs we might gain: shared knowledge of physics, medicine, even art, transforming human culture overnight. Yet the counterargument is stark. Historical precedent on Earth shows how encounters between unequal civilizations often end in exploitation, a pattern that could replay on a cosmic scale if we signal our presence to a species millennia ahead of us. This debate crystallized in 2015 when METI International transmitted radio messages to nearby stars, deliberately echoing the Arecibo experiment, but targeting systems just dozens of light years away, close enough for a reply within a human lifetime. Critics erupted, including figures like Elon Musk and Stephen Hawking, who likened it to shouting in a jungle filled with unknown predators. The concern isn't just hypothetical. In 1974, the Soviets broadcast a Morse code message toward a star cluster without international consensus, sparking outrage over who had the right to speak for Earth. Today, organizations like the International Academy of Astronautics have drafted non-binding protocols for post-detection response, but no global law enforces them. A single rogue actor, a billionaire, a nation, even an amateur astronomer with a powerful transmitter could theoretically trigger first contact without oversight. The dilemma deepens when we consider nearby exoplanets like Proxima Centauri b, a potentially habitable world just 4 light-years away. A message sent there could receive a reply within a decade, a tantalizingly short timescale that makes the risks feel immediate. Would we recognize a warning hidden in their response, or mistake hostility for hospitality? Some scientists propose sending mathematical smoke signals, benign puzzles, or universal constants that demonstrate intelligence without revealing our location. Others advocate for passive listening until we've developed defensive technologies, a cosmic version of look before you leap. Yet the most profound question isn't technical, it's philosophical. By choosing silence, do we condemn ourselves to cosmic isolation, forever wondering what might have been? Or by reaching out, do we gamble with a future we can't foresee? The stars might hold answers, but they won't whisper them gently. Every decision to transmit carries an echo of that first Arecibo broadcast, a binary bet on whether the universe is fundamentally kind or cold. And until we know for sure, the void between worlds isn't just filled with radio waves, it's filled with the weight of our own uncertainty. Among the thousands of exoplanets discovered so far, a select few orbit in what astronomers call the habitable zone, that perfect distance from their star where liquid water could pool on rocky surfaces. These worlds aren't just scientific curiosities, they're our best bets for finding neighbors. Take the TRAPPIST-1 system, 39 light-years away, with 7 Earth-sized planets crammed into orbits smaller than Mercury's. 3 of them sit squarely in the Goldilocks zone, their tight dance around a dim red dwarf creating tidal forces that might churn their interiors, fueling volcanic activity or even subsurface oceans. Then there's Proxima Centauri b, our closest exoplanet neighbor just 4 light-years distant, locked in a gravitational embrace with its faint star. Though bathed in harsh flares, its rocky composition and potential for liquid water make it a tantalizing target. Scientists have already beamed messages toward both systems, gambling that if someone's home, they might be listening too. But habitability alone isn't enough to guarantee a conversation. The universe is littered with planets where conditions could support life, yet silence reigns. That's why SETI newer approaches combine planetary science with signal hunting. Prioritizing stars older than our sun civilizations, there would have had more time to develop advanced technology. Systems like Kepler 442, home to a super-Earth orbiting a star nearly 3 billion years older than ours, top the list. Others focus on quiet stars, avoiding the deadly radiation flares of red dwarfs in favor of stable yellow suns like Tau Ceti, 12 light-years away, which hosts multiple planets in its habitable zone. The strategy mirrors searching for a needle in a cosmic haystack by first identifying which haystacks are most likely to contain needles. Yet even the most promising systems come with caveats. Proxima Centauri b's flares might strip atmospheres, while TRAPPIST-1 planets could be tidally locked, with one side scorched and the other frozen. Then there's the Eerie case of KIC 8462852, better known as Tabby's star. Its erratic dimming, observed by the Kepler telescope, sparked wild theories, from alien megastructures to swarms of comets. Years later, the likeliest explanation involves dust clouds, but the episode underscores how easily natural phenomena can masquerade as technosignatures. Historically, claims of contact have followed this roller coaster: initial excitement, then sober scrutiny. In 1967, the discovery of pulsars was nearly mistaken for an alien distress beacon. Decades later, the infamous Allen Telescope Array signal from Gliese 581 briefly matched expectations of an artificial transmission before being traced to a passing satellite. Each false alarm teaches the same lesson: the universe is weird enough to keep fooling us. Still, as our catalog of habitable worlds grows, so does the precision of the search. New telescopes like the James Webb Space Telescope are peering into exoplanet atmospheres, hunting for biosignatures like oxygen or methane, chemical hints that someone or something might already be home. The real twist: even if life thrives on these worlds, intelligence might be vanishingly rare. Earth took 4.5 billion years to produce a species capable of broadcasting into space. On other planets, evolution might stall at microbes, or leap beyond biology, entirely post-biological AIs communicating in ways we can't yet perceive. That's why the search isn't just about finding planets with water. It's about finding planets with time, enough millennia for life to stumble toward intelligence, and enough stability for that intelligence to survive its own technological adolescence. Until then, every new exoplanet is a question mark, a dial tone waiting to either connect or dissolve back into the static of the cosmos. History is littered with moments when humanity thought we'd finally heard from the stars, only to realize we were listening to cosmic pranks or our own wishful thinking. One of the earliest examples came in the summer of 1924, when astronomers at the U.S. Naval Observatory reported strange radio static they believed originated from Mars during its closest approach to Earth. Newspapers ran wild with claims of Martian broadcasts, igniting public imagination until it became clear the signals were merely atmospheric interference, bouncing off layers of Earth's ionosphere. Decades later, in 1967, the discovery of pulsars nearly repeated this pattern. Their unnervingly precise pulses had astronomers briefly considering the possibility of extraterrestrial beacons before identifying them as spinning neutron stars. These episodes reveal a recurring theme. When faced with the unknown, our brains instinctively reach for the most extraordinary explanation first. Modern technology hasn't made us immune to these missteps, it's just changed their flavor. Take the infamous alien megastructure star, KIC 8462852, whose erratic dimming in 2015 sparked theories of a Dyson sphere under construction. Even seasoned scientists entertain the idea, despite no concrete evidence. Then there's the 2017 Oumuamua incident, when a cigar-shaped interstellar object sparked debates over whether it was a natural asteroid or an artificial probe. Harvard astronomer Avi Loeb's controversial suggestion that it might be extraterrestrial technology made headlines worldwide, though most researchers attributed its odd acceleration to outgassing, a common cometary behavior. The line between healthy skepticism and sensationalism blurs easily when the stakes feel so profound. What drives this pattern? Psychologists call it patternicity, our brain's tendency to impose meaning on randomness, a survival mechanism turned cosmic liability. Combine that with anthropomorphism, projecting human-like intentions onto non-human phenomena, and you've got a recipe for interstellar false alarms. The infamous wow signal exemplifies this tension. Despite its tantalizing artificial-seeming properties, the lack of a repeat performance forces us to confront an uncomfortable truth. Extraordinary claims can't rely on single data points, no matter how thrilling. Hoaxes add another layer of noise to the signal hunt. In 1998, the Ummo affair, swept Europe when hundreds of scientists received elaborate letters supposedly from an alien civilization later exposed as an earthbound prank. More recently, viral, alien signal videos on social media routinely mix genuine astronomical phenomena with fabricated context, muddying public understanding. Each hoax erodes trust, making genuine discoveries harder to recognize, a lesson underscored by the infamous Morris Ketchum-Jessup UFO photo of 1952, later proven to be a hanging lamp photographed at an angle. Yet there's a silver lining to these false starts. Every misinterpretation forces science to refine its methods, separating cosmic wheat from chaff. The Allen Telescope Array's signal verification protocols, for instance, now require multiple observatories to confirm a detection before announcing it a direct response to past embarrassments. And perhaps that's the real lesson. The search for extraterrestrial intelligence isn't just about technology. It's about tempering our longing for connection with rigorous skepticism, learning to distinguish between what we hope is out there and what the evidence actually shows. Because in the end, the universe owes us neither silence nor answers, just the endless challenge of listening more carefully than before. From the moment our ancestors first gazed upward, the stars have been more than just points of light. They've been mirrors reflecting humanity's deepest yearnings. That primal pull to find others like us transcends mere curiosity. It's woven into our myths, our religions, and now our science. Ancient Sumerians told of sky gods descending in fiery chariots, while the Dogon tribe of Mali preserved astronomical knowledge they claimed came from celestial visitors. Fast forward to today, and the same impulse fuels blockbuster sci-fi films and billion-dollar SETI projects. This isn't just about aliens, it's about answering an existential question. In a universe so vast, could we truly be alone? Psychologists call this the loneliness hypothesis, the discomfort we feel at the thought of cosmic isolation. Our brains are wired for connection, so much so that we anthropomorphize planets and ascribe intention to random cosmic noise. The infamous LGM-1 pulsar discovery lays this bare. When Jocelyn Bell first detected its rhythm in 1967, the signal was so precise her team briefly labeled it "little green men" before uncovering its natural origin. That knee-jerk assumption reveals something profound. Given ambiguity, we'll always reach for the most meaningful explanation first. It's the same instinct that makes us see faces in clouds or hear whispers in static, a phenomenon called pareidolia, turbocharged by the stakes of cosmic contact. But why does the idea of extraterrestrial life hold such emotional weight? Philosophers argue it's tied to humanity's search for purpose. If life emerged independently elsewhere, it suggests we're part of a grand, universal pattern rather than a fluke. This hope fuels the Fermi paradox's tension. The louder the silence, the harder we listen. Even Carl Sagan admitted the possibility of two outcomes, one where we're the universe's only voice, and another where we're latecomers to a galactic conversation. Both are equally terrifying in their own ways. Science fiction amplifies these undercurrents, serving as a cultural rehearsal for first contact. Stories like Contact or Arrival don't just imagine aliens, they explore how meeting them would reshape our identity. Notably, these narratives often feature linguists and anthropologists rather than soldiers, revealing a collective optimism that advanced civilizations prioritize understanding over conquest. Yet real-world reactions to unexplained signals swing between extremes. When the WOW signal appeared, some scientists immediately drafted reply messages, while others, like Stephen Hawking, warned against shouting into the jungle. This dichotomy mirrors our own evolutionary past. simultaneously craving connection and fearing the unknown. The line between science and speculation blurs most in cases like Tabby's star, where unusual dimming sparked legitimate astrophysical debate alongside wild theories. Here's the irony: rigorous skepticism is what makes SETI credible, yet that same skepticism can feel like it's dousing the very hope that fuels the search. Perhaps that's the tightrope we walk, balancing the thrill of possibility with the discipline of evidence, knowing the greatest discovery in history could look, at first, like a blip we'd normally ignore. After all, if ET ever does call, they probably won't say hello in a way we expect. They might not say it at all, but as long as that uncertainty exists, we'll keep scanning the static, because the alternative, accepting silence as final, feels like surrender. And humanity, for all its flaws, has never been good at giving up. In the quiet pre-dawn hours of November 1967, Cambridge researcher Jocelyn Bell noticed something odd in her radio telescope data: a series of pulses arriving every 1.337 seconds with precision rivaling atomic clocks. Her team's first scribbled notation, LGM-1, shorthand for Little Green Men, the signal's unnatural regularity, had scientists briefly entertaining an electrifying possibility. Were they eavesdropping on an alien timekeeping system, a cosmic navigation beacon, or even an interstellar distress call? The truth, when it came, was humbling. LGM-1 wasn't ET phoning home. It was the death throes of a spinning neutron star, a celestial object so dense its crushed core could beam radio waves across the galaxy like a lighthouse. The discovery, later renamed Pulsar PSRB 1919+21, became one of astronomy's greatest accidental breakthroughs and a sobering reminder of how easily nature can impersonate intelligence. Yet the lesson cuts both ways. Just because LGM-1 was natural doesn't mean every peculiar signal will be. Fast forward to 2020, when Breakthrough Listen detected BLC-1, a narrowband radio emission seemingly originating from Proxima Centauri, the closest star system to Earth. Unlike the pulsar's metronomic ticks, this signal drifted in frequency the way a moving transmitter would, and it appeared only when telescopes pointed at the star, vanishing when aimed elsewhere. The parallels to the WOW signal were immediate, but modern verification protocols prevented premature celebration. Months of analysis revealed a more mundane culprit: human-made radio interference, likely from a passing satellite or surface electronics. Still, the episode underscored how far we've come since LGM-1. Today's astronomers no longer circle printouts in red pen. They deploy machine learning to sift through millions of signals, cross-referencing detections with satellite logs and atmospheric conditions. The irony: our tools for filtering out false alarms might also be blinding us to truly alien messages. Pulsars taught us to expect cosmic signals that are either chaotic or perfectly periodic, but what if extraterrestrial communication lives in the messy middle? Imagine a civilization encoding information in signals that pulse almost regularly, their slight variations carrying meaning. To our algorithms, such transmissions might look like noise, dismissed alongside solar flares and equipment glitches. This paradox haunts every modern SETI effort. The stricter our criteria for artificiality, the greater the risk of filtering out the very signals we seek. Perhaps the most enduring legacy of LGM-1 isn't just caution, it's the way it reshaped our definition of alien. Before pulsars, few imagined natural objects could produce such engineered-seeming rhythms. Now, we know the cosmos is full of phenomena that defy intuition: magnetars cracking like cosmic whips, black holes ringing spacetime like bells, and rogue planets emitting radio whispers as they drift through the void. Each discovery expands the spectrum of what's possible, blurring the line between nature's artistry and deliberate design. The next time we detect a signal that stops us in our tracks, it might not be a choice between natural or alien, but a third option we haven't even conceived yet. And that's the real lesson of LGM-1. The universe is far stranger than our assumptions, and its greatest revelations often come dressed as disappointments at first. In 2020, a signal from Proxima Centauri, our Sun's closest stellar neighbor, sent ripples through the scientific community. Detected by Breakthrough Listens Parkes telescope in Australia, this narrowband radio emission, dubbed BLC-1, ticked every box for an artificial transmission. It appeared only when the telescope pointed toward Proxima Centauri, vanishing when aimed elsewhere, a telltale sign of a localized source. Even more intriguing, the signal drifted in frequency, mimicking the Doppler shift you'd expect from a transmitter on a moving planet. For a brief, electrifying moment, the possibility hung in the air. Had we finally intercepted a technosignature from just 4 light-years away, the excitement was tempered by caution. Modern SETI protocols demand exhaustive vetting, and BLC-1 underwent a forensic dissection. Researchers cross-referenced the signal with satellite trajectories, ruled out aircraft and ground interference, and even checked for malfunctions in the telescope itself. Months later, the likeliest explanation emerged: human-made radio interference, possibly from a passing satellite or faulty electronic device on Earth. The letdown was palpable, but the episode wasn't a failure. It was a masterclass in scientific rigor. Unlike the WOW signal's unresolved mystery, BLC-1 showcased how far our verification processes have come, with algorithms and multi-telescope coordination now capable of tracing even the most elusive false alarms. Yet the case raises a provocative question. What if some signals are alien, but so bizarrely encoded or transient that our current methods dismiss them as noise? Imagine a civilization broadcasting in pulses that mimic stellar flares or embedding messages in the polarization of light waves, techniques we're only beginning to explore. The very filters designed to weed out human interference might accidentally screen out the truth. Proxima Centauri's false alarm serves as a reminder: the universe is under no obligation to communicate in ways we find convenient. Every dead end forces us to refine our tools, but it also nudges us to stay open to the possibility that first contact won't arrive as a clean, decipherable signal. It might come as static we've been ignoring for decades, a whisper hiding in plain sight, waiting for the right moment to be heard. Radio waves might be humanity's first attempt at cosmic communication, but what if advanced civilizations have long since moved on? The search for extraterrestrial intelligence is evolving beyond traditional radio signals, hunting for subtler fingerprints of technology, clues we call technosignatures. Picture a civilization thousands or even millions of years ahead of us. They might harness energy by building Dyson spheres, vast megastructures enveloping stars to capture their power, leaking telltale infrared heat we could detect. Or perhaps they communicate with tightly focused laser pulses, invisible to radio telescopes but glaringly obvious to optical sensors trained on the right frequencies. Then there's the atmosphere itself. Just as human industry has laced Earth's air with carbon dioxide and chlorofluorocarbons, an alien society might leave chemical traces in their planet's skies, pollutants, or artificial gases with no natural explanation. Astronomers already scan exoplanet atmospheres for biosignatures like oxygen, Finding synthetic compounds like nitrogen oxides or even refrigerant chemicals could hint at something far more deliberate. The real challenge, distinguishing industrial byproducts from rare geological processes. A whiff of chlorofluorocarbons on a distant world might be our first evidence that we're not alone, or just a sign of volcanic activity we don't yet understand. Few cases capture this ambiguity better than Tabby's star, officially known as KIC 8462852. This bizarre object dimmed erratically by up to 22%, far too much for a planet passing in front, and stayed dim for days or weeks at a time. Speculation ran wild. Was it surrounded by a swarm of giant solar panels, a partially built Dyson sphere? Years later, the leading theory points to clouds of dust, possibly from shattered comets or planetary collisions. Yet the episode remains a cautionary tale. The universe is full of phenomena we haven't seen before, and the line between natural oddity and alien engineering blurs easily when staring into the unknown. New tools are sharpening our vision. The James Webb Space Telescope can sniff out atmospheric chemicals light years away, while projects like Breakthrough Listen now scan for laser flashes alongside radio waves. Some researchers even propose hunting for city lights on the night side of exoplanets, glowing evidence of sprawling metropolises. The irony, the most advanced civilizations might leave the faintest footprints. A society mastering fusion or dark energy could operate with near-zero waste heat, rendering their presence nearly invisible to our current instruments. The search for technosignatures forces us to confront a humbling truth. We're like islanders scanning the horizon for smoke signals while the rest of the world texts under our noses. Alien technology might not announce itself in ways we expect or can even perceive yet, but that's the thrill of the hunt. Every unexplained atmospheric molecule, every anomalous dimming event, every pulse of light that doesn't quite fit could be the first breadcrumb leading to an answer. Or it could be another cosmic illusion, reminding us that the universe is always one step ahead. Either way, the game's afoot, and the rules are still being written. When astronomers first noticed KIC 8462852, better known as Tabby's star, its behavior shattered expectations. Unlike ordinary stars, which dim predictably when planets pass in front, this one flickered erratically, sometimes plunging in brightness by a staggering 22% before rebounding. The irregularities defied all known explanations, sparking a frenzy of speculation. Could this be evidence of a Dyson sphere, a hypothetical alien megastructure designed to harness a star's energy? The idea wasn't entirely far-fetched. After all, a civilization advanced enough to build such a thing might leave behind exactly this kind of fingerprint, an artificial swarm of solar collectors blotting out light in unpredictable patterns. But science thrives on ruling out the extraordinary before embracing it. Over years of observation, a more mundane culprit emerged: dust, not just any dust, but vast clouds of it, possibly from comets or planetary collisions, drifting across the star's face in uneven waves. Infrared observations supported this, showing heat signatures consistent with fine particles rather than solid megastructures. Yet even this explanation leaves gaps. The sheer amount of dust required and its peculiar distribution still don't fit neatly into existing models of stellar systems. Tabby's star remains a cosmic oddity, a reminder that the universe often refuses to follow our scripts. What makes this case so fascinating isn't just the science, it's the psychology behind the hunt. The mere possibility of alien megastructures ignited imaginations worldwide, proving how deeply we yearn for evidence of other builders in the cosmos. And while the dust theory may lack the thrill of extraterrestrial engineers, it's no less significant. This star challenges our understanding of how planetary systems evolve, suggesting violent, chaotic processes we've yet to fully comprehend. Every time it dims, it whispers a question: are we missing something even more fundamental? Now, the search expands beyond stars altogether. Rogue planets, worlds untethered to any sun, drifting through the cold void, might seem like unlikely places to find signals. But consider this: a civilization facing extinction might flee their dying star aboard a massive nomadic world, harnessing geothermal or nuclear energy to survive. Others could use these dark travelers as stealthy interstellar probes, their very isolation making them ideal for covert communication. New telescopes, like the upcoming Nancy Grace Roman Space Telescope, are poised to spot thousands of these rogue worlds. Who knows what whispers might hitch a ride on their silent journeys? The lesson of Tabby's star is clear. Sometimes, the most profound discoveries begin with a flicker, and the courage to ask what's causing it, even when the answer isn't what we hoped. Rogue planets drift through the interstellar darkness like cosmic ghosts, worlds ripped from their parent stars by gravitational chaos, or born alone in the void. Without a sun to warm them, their surfaces freeze at temperatures near absolute zero, yet beneath icy crusts, oceans of liquid water might persist, heated by tidal forces or radioactive decay. These hidden seas could teem with extremophile life, organisms thriving in conditions we once thought impossible. But what if some rogue planets harbor more than microbes? What if, in the eternal night between stars, intelligence found a way? The idea isn't as far-fetched as it sounds. Subsurface oceans on moons like Europa and Enceladus already hint at life's potential to flourish without sunlight. A rogue planet with similar conditions and millennia to evolve might host civilizations adapted to perpetual darkness, their technology powered by geothermal vents or nuclear fission. The catch: detecting them. Traditional SETI relies on spotting radio leaks or deliberate transmissions, but a nomad world's inhabitants might communicate through neutrino beams or quantum entanglement, mediums nearly invisible to our current telescopes. Even their energy signatures would differ. Waste heat from underground cities would be trapped under miles of ice, leaving no infrared trace. Then there's the mystery of rogue planet infrared signals. In 2021, astronomers scanning the darkest regions of space detected unexplained thermal glows, faint heat signatures with no obvious source. Some theorize these could be orphaned worlds, their cores still warm from formation or internal processes. Others wonder, might an advanced civilization deliberately vent heat to signal their presence? It's a long shot, but the sheer number of rogue planets estimates suggest there could be trillions drifting through the Milky Way, means even unlikely possibilities demand attention. The hunt for these dark messengers is pushing technology to its limits. Gravitational microlensing, which detects planets by how their gravity bends light from distant stars, has spotted a handful of candidates. Future telescopes like NASA's Nancy Grace Roman Space Telescope will expand the search exponentially. But to eavesdrop on potential inhabitants, we'd need sensors capable of picking up non-electromagnetic whispers, perhaps arrays tuned to catch gravitational waves or bursts of neutrinos, the universe's stealthiest carriers of information. Here's the tantalizing thought: rogue planets might be the ultimate cosmic eavesdroppers. Floating unseen between stars, they could serve as relay stations for interstellar communication, their icy shells shielding delicate equipment from radiation. Or they might be arcs, entire civilizations fleeing dying stars, carrying their history into the abyss. The silence of these nomad worlds isn't proof they're empty. It's an invitation to listen differently, to consider that the greatest conversations in the universe might be happening in frequencies we're only beginning to imagine. After all, in the endless dark, even a whisper can travel forever. Infrared astronomy opens a window into the universe's hidden energy heat signatures invisible to the naked eye, but screaming with information. For decades, scientists have scanned the cosmos for unexplained thermal glows, theorizing that advanced civilizations might leave behind a telltale infrared footprint. The logic is simple. Any society harnessing vast amounts of energy, whether through Dyson swarms, industrial megastructures, or planet-scale computing, would inevitably radiate waste heat. This isn't science fiction, it's basic thermodynamics, yet despite decades of searching, from the pioneering era's satellite in the 1980s to modern telescopes like WISE, no definitive technosignatures have emerged. The absence raises a haunting question. Are we missing something fundamental, or is the cosmos as empty as it seems? Take the case of KIC 4152567, a star whose infrared excess puzzled astronomers for years. Initial excitement over its unusual heat pattern led to speculation about alien engineering, perhaps a partially completed Dyson sphere leaking thermal energy. But closer inspection revealed a more prosaic culprit, a colossal ring of warm dust, likely the aftermath of planetary collisions. Similar false alarms dot the history of infrared SETI, each a reminder that nature's workshop can forge heat signatures indistinguishable from artificial ones. Dust clouds, young stellar nurseries, even rare cosmic events like quark nova remnants, all mimic the infrared profiles we might expect from advanced technology. But what if the problem isn't just cosmic imposters? Some researchers argue our search parameters are too narrow. We assume alien civilizations would operate at temperatures similar to our own machinery, radiating waste heat in the mid-infrared range. Yet a society mastering nanotechnology or quantum energy harvesting might operate at drastically different efficiencies, emitting heat patterns we wouldn't recognize as artificial. Imagine searching for candle flames in a world where everyone uses LEDs. You'd miss the civilization right in front of you. There's another, more unsettling possibility. The great filter might not lie ahead of us, but behind. The absence of infrared technosignatures could suggest intelligent life rarely survives long enough to harness stellar-scale energy. Or perhaps advanced civilizations evolve beyond detectable heat emissions entirely, transitioning to forms of energy we can't yet conceive. Dark matter manipulation, zero-point energy extraction, these aren't just plot devices from sci-fi, but legitimate theoretical frontiers that, if mastered, would leave no infrared trail for us to follow. The search isn't over. New initiatives like the Galileo project are revisiting old infrared datasets with machine learning, hunting for anomalies dismissed as noise in prior decades. Others propose looking for anti-signatures, stars inexplicably lacking expected infrared radiation, as if something were blocking or repurposing their energy. The answers, if they exist, may not come from a eureka, a moment, but from patient accumulation of tiny irregularities, each insignificant alone but revolutionary in aggregate. Until then, the infrared silence speaks volumes not necessarily about the absence of others, but about the limits of our own imagination. The universe's greatest conversations might be happening in a language of heat we're only beginning to decode. Buried within decades of cosmic static, overlooked whispers might hold the key to humanity's oldest question. Across the globe, researchers are now feeding vast archives of radio telescope data into advanced AI systems, training them to sift through background noise for anomalies too subtle for human analysts to catch. It's like replaying every second of a decades-long cosmic symphony, only this time with algorithms fine-tuned to pick out a single off-key note. One such project, led by the SETI Institute in 2021, reanalyzed over 2 million signals from the Kepler star field using machine learning. The result, 8 previously dismissed candidates exhibiting strange, non-natural characteristics, narrowband frequencies that slipped past earlier filters. None have repeated, but the sheer fact they emerged from old date proves how much we might have missed. The challenge lies in distinguishing meaningful patterns from chaos. Traditional SETI searches focused on narrowband signals, clean, artificial-looking spikes against the broadband noise of natural phenomena. But what if alien transmissions aren't so tidy? A civilization might encode messages in seemingly random bursts, relying on mathematical keys buried in the timing or polarization. AI excels at finding these hidden fingerprints, uncovering structure in what looks like static. In 2023, a team at the University of Toronto applied neural networks to archival data from the Green Bank telescope, flagging dozens of signals with peculiar phase variations, subtle twists in their wave patterns that don't align with known astrophysical sources. Follow-up observations came up empty, but the method itself could revolutionize how we listen. Then there's the tantalizing case of peritons. These ultra-brief microwave bursts, first noted in the 1970s, were long dismissed as terrestrial interference, possibly from military radar or satellites. But a 2020 re-examination revealed clusters of peritons recorded simultaneously by telescopes on different continents, ruling out local sources. Their origin remains unknown, though theories range from atmospheric plasma events to whisperate leakage from clandestine space-based technology. Whether natural or not, the rediscovery underscores how even solved data can harbor unsolved riddles. The real game changer, crowdsourcing cosmic detective work. Projects like SETI at home once harnessed millions of home computers to analyze signals. Now, initiatives like Breakthrough Listens, Open Data Archive, invite amateur astronomers and AI enthusiasts worldwide to comb through petabytes of observations. In 2022, a high school student in Norway spotted a repeating pattern in data from the Rarity array, later identified as a previously unknown pulsar. While not alien, the find proved that fresh eyes, human or artificial, can extract treasures from noise. The next breakthrough might not come from a new signal at all, but from an old one revisited with sharper tools. Imagine if the WOW signal had been recorded with today's high-resolution spectrometers. We might have detected modulations or harmonics invisible to 1970s technology. That's the promise of archival archaeology. Every byte of old data is a time capsule, preserving cosmic whispers we lacked the means to hear the first time around. As machine learning evolves, so does our ability to interrogate the past, turning yesterday's dead ends into tomorrow's revelations. The silence of space isn't necessarily empty, just encrypted in ways we're finally learning to crack. The next decade could rewrite the book on interstellar eavesdropping, as revolutionary telescopes come online, instruments so powerful they might hear whispers we've been missing for centuries. Leading the charge is the Square Kilometre Array, or SKA, a sprawling network of antennas across South Africa and Australia that will scan the sky with 50 times the sensitivity of current arrays. Unlike single-dish telescopes, SKA's thousands of linked receptors can pinpoint signals across vast swaths of the universe simultaneously, teasing out patterns from cosmic noise like never before. Its first light, expected in 2028, might reveal signals buried in data we've dismissed as static for generations. But Earth-bound instruments have limits: atmospheric interference, radio pollution from our own civilization, which is why projects like the Breakthrough Starshot Initiative propose space-based observatories. Imagine telescopes floating beyond the moon's orbit, free from Earth's electronic chatter, their ears pressed to the cosmos without distraction. Artificial intelligence is the game changer no one saw coming. Traditional SETI searches were like panning for gold in a river, slow, laborious, and limited by human attention spans. Now, machine learning algorithms ingest petabytes of telescope data, hunting for aberrations that defy natural explanations. At the University of California, Berkeley, an AI trained on simulated alien signals recently identified 8 previously overlooked candidates in archival data. None confirmed yet, but the approach itself is revolutionary. These systems don't just look for narrowband radio spikes. They analyze signal drift, polarization twists, even statistical irregularities that might encode information. The real breakthrough, adaptive learning. Future AI could redesign its own search parameters mid-scan, pivoting to investigate anomalies in real time like a detective who changes their questioning based on a suspect's microexpressions. Private funding is injecting fresh momentum into the hunt. Billionaires like Yuri Milner and Elon Musk aren't just writing checks, they're challenging conventional wisdom. Milner's Breakthrough Listen project has already scanned more stars than all previous SETI efforts combined, while Musk's Starlink satellites, controversial among astronomers for light pollution, could ironically become part of the solution. Engineers are testing ways to repurpose their vast orbital network as a makeshift radio telescope, turning what was once interference into an asset. Even citizen scientists are joining the fray through platforms like SETI at Home, where home computers worldwide crunch telescope data during downtime. Yet for all this innovation, the fundamental question lingers: will sharper tools unveil truths, or simply reveal how much we've underestimated the universe's complexity? The SKA might detect signals from civilizations that perished millennia ago, their messages only now reaching us. AI could decode a transmission only to find it's a cosmic, out-of-office auto-reply, an ancient beacon with no one left to listen. Or perhaps we'll discover that advanced societies communicate through quantum entanglement or dark matter interactions, mediums we're only beginning to fathom. The silence isn't a verdict, it's an invitation to build better ears. And as the next generation of telescopes powers up and algorithms grow wiser, one thing's certain: humanity's listening session with the universe is just getting started. The hunt for cosmic neighbors isn't just the domain of government agencies and university labs, and more private dollars are now fueling some of the most ambitious searches in history. Leading the charge is Breakthrough Listen, a $100 million initiative bankrolled by billionaire Yuri Milner. Launched in 2016, this project dwarfs traditional SETI efforts in scale, scanning over 1 million nearby stars and 100 galaxies across 10 billion radio channels. Unlike older programs that relied on borrowed telescope time, Breakthrough Listen commands dedicated access to world-class instruments like the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia. The result: a fire hose of data analyzed by AI systems capable of spotting anomalies human eyes might miss. But this isn't just about throwing money at the problem. The project's open data philosophy invites global collaboration, with raw observations available to anyone, amateurs and academics alike, democratizing the search like never before. Yet private funding brings its own controversies. Critics worry the allure of headlines could prioritize splashy announcements over rigorous science. Remember the 2020 signal from Proxima Centauri. Breakthrough Listen's initial excitement over the seemingly artificial transmission gave way to months of painstaking debunking, a process less glamorous than the initial, possible alien contact narrative. Some astronomers argue this roller coaster risks eroding public trust, turning legitimate research into a boy who cried wolf scenario. Others counter that without private backers, SETI would still be scraping by on shoestring budgets, its telescopes sitting idle for lack of funding. The reality likely lies between. Private initiatives amplify the search, but their flashier profile demands extra vigilance against false alarms. Then there's the elephant in the room, the question of visitation. While Breakthrough Listen scans for distant signals, other billionaire-backed ventures like Blink Astro hunt for physical evidence closer to home. Using networks of high-resolution cameras, they track unexplained aerial phenomena, filtering out drones and weather balloons in search of anomalies that defy conventional explanation. The scientific community remains deeply divided. Harvard's Avi Loeb made waves arguing that interstellar objects like Oumuamua could be artificial probes, while mainstream astronomers dismiss such claims as sensationalism. The tension reflects a broader dilemma. How do we balance open-minded inquiry with the discipline to demand extraordinary evidence for extraordinary claims? What unites these efforts, public and private, is a shared recognition of the stakes. Whether scanning radio waves or analyzing UFO footage, we're grappling with the same existential itch, the need to know if we're alone. Breakthrough Listen's approach has already expanded the search space exponentially, cataloging hundreds of unexplained signals for further study. Even if 99.9% prove to be cosmic static, the remaining fraction could hold the key. As for visitation, the lack of definitive proof hasn't stopped governments from declassifying military footage or Congress from holding hearings on unidentified phenomena. The truth might not be lurking in one dataset but scattered across many, a puzzle waiting for the right pieces to snap together. Until then, the private sector's role is clear: fund the tools, share the data, and keep the conversation grounded in science, not spectacle. Because whether the answers come from a billionaire's telescope or a graduate student's algorithm, the discovery, if it ever comes, will belong to all of us. The skies have always been a canvas for our wonder and our fears. In recent years, declassified military footage and government reports on UAPs, or unidentified aerial phenomena, have thrust age-old questions back into the spotlight. Are we witnessing advanced foreign drones, atmospheric oddities, or something far more extraordinary? The truth, as usual, lies somewhere in the static between fact and speculation. Take the now famous Tic Tac incident recorded by U.S. Navy pilots in 2004. An oblong object, devoid of wings or exhaust, danced erratically at hypersonic speeds before vanishing, a performance that defied known aerodynamics. Skeptics point to sensor glitches or experimental technology, but the pilot's first-hand accounts add weight to the mystery. Then there's the 2020 Pentagon report, which cataloged 144 UAP sightings, admitting 21 had no plausible explanation. Yet for every tantalizing case, there are hundreds with mundane origins. Weather balloons, military flares, even flocks of birds can morph into alien craft under the right conditions. The planet Venus, dazzlingly bright near the horizon, has fooled countless observers, while rare atmospheric phenomena like ball lightning or ice crystal refraction create optical illusions that baffle even experts. The key is in the data, or often the lack of it. Most UAP footage suffers from shaky cameras, poor resolution, or missing context, turning unidentified objects into Rorschach tests for our imagination. That's why scientists demand repeatable evidence, radar tracks, infrared signatures, and multiple eyewitnesses aligned like stars in a constellation. What's fascinating isn't just the unresolved cases, but why they linger in our collective psyche. The idea of visitors from the stars touches something primal, a mix of curiosity and vulnerability. If even a fraction of these sightings represent extraterrestrial technology, the implications would rewrite history. But the quieter possibility is equally profound, that Earth's atmosphere still holds secrets we've yet to unravel. Plasma formations, exotic propulsion tests, or undiscovered natural phenomena could explain many UAPs without invoking little green men. As we stand at the edge of this mystery, one thing becomes clear. Whether the truth is terrestrial or otherwise, the search itself reflects humanity's restless urge to look up and ask. Every unexplained blip on a radar screen, every pilot's baffled testimony, is a reminder that the universe refuses to be neatly cataloged. And perhaps that's the real gift of these enigmas, not answers, but the humility to admit how much we still have left to discover, right here in our own sky. The silence of the cosmos isn't just a scientific puzzle, it's a mirror reflecting humanity's deepest existential questions. For centuries, we've operated under the Copernican principle, the idea that Earth holds no special place in the universe. If life arose here, the logic goes, it should flourish elsewhere under similar conditions. Yet the more we search, the more we confront an unsettling alternative. What if we're the exception rather than the rule? This is the heart of the rare Earth hypothesis, which argues that the chain of events leading to complex life, a stable star, a protective moon, plate tectonics, even the right galactic neighborhood, might be so improbable that intelligent life is vanishingly rare. The debate splits astronomers like few others. On one side, optimists point to the sheer number of exoplanets, trillions in our galaxy alone, as statistical inevitability. On the other, skeptics note that after 4 billion years, Earth has produced exactly one spacefaring species. The truth might lie in the signals we've already caught but misunderstood. Take the WOW signal's eerie perfection, a narrowband radio burst that checks every box for artificiality yet refuses to repeat. Could it have been a cosmic flare from a dying star, or a one-time beacon from a civilization that flickered out millennia ago? The ambiguity itself is telling. Every unexplained signal becomes a Rorschach test for our cosmic loneliness. Some, like the repeating fast radio bursts from distant galaxies, hint at natural processes we don't yet grasp. Others, like the infamous BLC-1 from Proxima Centauri, tease us with possibilities before revealing earthly origins. These near misses expose a deeper tension. We long for connection, but fear what confirmation might mean. If we're not alone, are we pioneers or latecomers to a galactic conversation? If we are alone, does that make us custodians of life's flame or accidental orphans in an indifferent universe? Philosophy and astronomy collide in the Fermi paradox's unsettling silence. Enrico Fermi's famous question, "Where is everybody?" haunts every signal search. One theory suggests advanced civilizations inevitably self-destruct, their technologies outpacing their wisdom. Another proposes they transcend physical forms, uploading consciousness into quantum substrates we can't detect. The darkest interpretation, that something or someone systematically silences emerging intelligences before they can broadcast, yet there's poetry in the search itself. Whether poring over data from the square-kilometer array or debating the ethics of METI transmissions, humanity is performing something radical, turning our instruments outward, choosing curiosity over fear. As we circle back to those enigmatic signals, the ones that quickened pulses and spawned countless theories, their true significance may not lie in their origins, but in how they've reshaped us. The WOW signal, FRB 121102's defiant repetitions, even Tabby's star's mysterious dimming, each is a cosmic whisper asking us to reconsider our place in the story. Perhaps the answer to "Are we alone?" isn't a binary yes or no, but an invitation to keep listening with equal parts rigor and wonder. After all, the universe hasn't stopped speaking. We're just beginning to understand the language. Among the countless blips and bursts that have crackled through telescopes over the decades, a handful stand out like cosmic flares in the dark, signals so peculiar they've etched themselves into the annals of interstellar mystery. Take the infamous WOW signal, that 72-second radio scream from Sagittarius in 1977, its intensity spiking 30 times louder than the cosmic background before vanishing without a trace. Despite decades of follow-up scans, it's never repeated, leaving astronomers torn between two possibilities. Was it a fleeting natural anomaly, like a comet's hydrogen cloud reflecting sunlight, or a one-time transmission from a civilization that briefly flickered onto our radar? Then there's its modern counterpart, the tantalizing BLC-1 from Proxima Centauri in 2020, a narrowband signal with the precise frequency drift of an artificial transmitter, only to be traced months later to human interference. These false alarms aren't failures, they're mile markers showing how far our verification processes have come. Shift the focus to deep space, and the repeating fast radio burst FRB 121102 rewrites the rules entirely. Unlike most FRBs that flash once and disappear, this one pulses sporadically from a dwarf galaxy 3 billion light-years away, its emissions twisting in polarized patterns that suggest an intensely magnetized environment. Some researchers cling to the magnetar explanation, a neutron star with a magnetic field so strong it regularly cracks open, releasing energy tsunamis. Others wonder if we're glimpsing something more deliberate, like a malfunctioning alien beacon or even a power source for megascale engineering. The truth might lie beyond our current physics. After all, a civilization mastering black hole energy would operate on principles we're just beginning to imagine. But not all cosmic oddities are created equal. The infamous alien megastructure star, KIC 8462852, captivated the world with its erratic dimming until dust clouds emerged as the likely culprit. Similarly, the pulsar PSRB 1911+21, initially mistaken for extraterrestrial signals in 1967, became a cornerstone of astrophysics once its true nature as a spinning neutron star was revealed. These cases share a common lesson. The universe is a master of disguise, capable of mimicking intelligence with natural phenomena. Yet their legacy endures because each time we debunk a signal, we refine our ability to recognize the real thing. Now, as next-generation tools like the square-kilometer array prepare to scan the skies with unprecedented precision, The question isn't just whether these signals were natural or artificial, it's whether we've been asking the right questions at all. Maybe the messages we seek aren't in radio waves, but in neutrino fluctuations or gravitational ripples. Perhaps they're not even meant for us, but for civilizations with senses and technologies we can't yet fathom. The beauty of these cosmic riddles lies in their duality. Every dead end forces us to expand the search, and every unexplained whisper reminds us that the universe always has another card to play. The next breakthrough might not come from a new signal, but from reevaluating an old one with fresh eyes, or recognizing that the conversation has been happening all along, just not in the language we expected. The 2030s stand poised on the knife's edge of possibility, a decade that could shatter our cosmic solitude or deepen the silence. With telescopes like the Square Kilometre Array coming online and AI sifting through decades of static with inhuman precision, the odds of detection have never been higher. Optimists envision a watershed moment, an unmistakable signal decoded into mathematical primes, or a repeating pattern that defies astrophysical explanation. Picture the scene: observatories worldwide cross-verifying the data, governments scrambling to craft a response, and humanity collectively holding its breath as the first confirmed "hello" from the stars rewrites textbooks overnight. Some scientists speculate such a discovery could trigger a global renaissance, uniting nations under the staggering realization that we're not alone. Yet the era could just as easily deliver ambiguity rather than answers. Even with sensors 1,000 times more sensitive, we might uncover only more tantalizing near misses, signals that flicker and fade before confirmation, or technosignatures too bizarre to classify. Dr. Jill Tarter, a trailblazer in SETI research, warns that the search is a marathon, not a sprint. Advanced civilizations might communicate via neutrino pulses or quantum networks, leaving no trace in the radio spectrum we've spent decades monitoring. There's also the sobering scenario that the Fermi paradox's great filter lies ahead, a galactic graveyard of civilizations that never survived their technological adolescence. The silence, in this case, wouldn't be empty but ominous. The societal impact of either outcome is equally profound. A confirmed signal would force humanity to confront existential questions. Do we reply, risking exposure to unknown motives? How would religions, economies, and political systems absorb the news? Historians point to the 1969 moon landing as a preview, a moment that briefly united billions in awe, but soon faded into routine. A detection might follow a similar arc, initial euphoria giving way to the grind of interpretation. Conversely, another decade of silence could fuel the rare Earth hypothesis, the idea that life's leap to intelligence is so improbable, we might truly be the universe's sole witnesses. Technological leaps will redefine the hunt regardless. Projects like Breakthrough Starshot aim to launch miniature probes to Alpha Centauri within the next 20 years, while quantum sensors may soon sniff out gravitational anomalies or dark matter interactions that current instruments miss. The wild card, machine learning's uncanny ability to find patterns in noise. An AI trained on hypothetical alien languages might one day flag a signal we'd have dismissed as cosmic static, revealing a conversation that's been flowing around us all along. The only certainty is that the search itself transforms us. Every scan of the sky, every debunked false alarm, every upgrade to our cosmic ears refines not just our technology but our humility. Whether the 2030s deliver contact or more questions, the act of listening stitches humanity into a grander narrative, one where we're either the universe's first whisper or latecomers to a dialogue beyond our grasp. And that tension between hope and patience, between reaching out and waiting, is what makes this decade not just a chapter in astronomy, but a mirror for who we are and who we aspire to become. The scientific community is anything but unanimous when it comes to interstellar signals. Ask 10 experts, and you'll get 12 opinions. Take Dr. Jill Tarter, co-founder of the SETI Institute, and the real-life inspiration for Jodie Foster's character in Contact. After decades of scanning the cosmos, she remains cautiously optimistic, comparing the search to looking for fish in Earth's oceans by scooping up a single glass of water. The universe, she argues, is simply too vast to draw conclusions from silence alone. On the opposite end of the spectrum sits astrophysicist David Kipping, who likens the hunt for alien signals to searching for a needle in a haystack when we're not even sure needles exist. His skepticism stems from the Fermi paradox's chilling implication: if life were common, why haven't we found any traces? Yet between these poles lies a chorus of nuanced perspectives. Dr. Avi Loeb, the Harvard astronomer behind the controversial Oumuamua hypothesis, champions what he calls cosmic humility, the idea that dismissing unexplained phenomena as natural too quickly risks blinding us to genuine breakthroughs. He points to fast radio bursts as prime examples. When nature mimics technology so precisely, shouldn't we at least consider the possibility we're not the only players in the game? Meanwhile, astrobiologist Dr. Sarah Seeger advocates for a broader approach. We've been fixated on radio waves, she notes, but advanced civilizations might communicate through biosignatures, industrial gases in exoplanet atmospheres, or even artificial photosynthesis signatures we've yet to imagine. The divide extends to the ethics of active messaging. SETI pioneer Dr. Frank Drake, who penned the iconic Drake equation, famously endorsed broadcasting, arguing that any species capable of interstellar communication would likely share curiosity, not hostility. But Lord Martin Rees, the UK's Astronomer Royal, counters with a grim analogy: banging on the jungle door unannounced rarely ends well for the smaller creature. This tension plays out in projects like METI, Messaging Extraterrestrial Intelligence, which continues sending targeted transmissions despite warnings from figures like Stephen Hawking. What unites these voices is a shared reverence for the unknown. Whether they lean toward hope or skepticism, each researcher underscores the same truth: the search for cosmic neighbors isn't just about aliens, it's about redefining humanity's place in the universe. Every unexplained signal, every heated debate, every technological leap reminds us that science thrives not on answers, but on questions that stretch the boundaries of imagination. And perhaps that's the real allure of these mysteries, not the promise of contact, but the way the void keeps us reaching, wondering, and growing. After all, the stars have always been more than distant suns, they're mirrors reflecting our endless capacity to ask, what if? The search for cosmic whispers does far more than satisfy scientific curiosity. It reshapes who we are as a species. Think about it. Every unexplained signal, every telescope pointed skyward, represents humanity at its most hopeful and vulnerable. This isn't just astronomy, it's a mirror reflecting our deepest yearning to belong to something grander. Artists from Kubrick to Bowie have drawn from this wellspring, crafting films, music, and literature that ask what contact might mean for our identity. Consider Close Encounters of the Third Kind's haunting five-note motif, or the cerebral puzzles of Arrival. These stories don't just entertain, they prepare us emotionally for a revelation that could come any day or never at all. But the impact runs deeper than pop culture. The hunt for extraterrestrial intelligence has repeatedly united rival nations in shared purpose. During the Cold War, Soviet and American scientists secretly collaborated on SETI protocols, proving that the stars could inspire cooperation even when earthly politics drove division. Today, projects like Breakthrough Listen pool resources across continents, turning what was once solitary speculation into a global endeavor. There's poetry in that, a species fractious by nature, yet willing to set aside differences for the chance to whisper, "Are you out there?" Then there's the technological spillover. The algorithms developed to sift cosmic static now diagnose diseases from medical scans, while radio telescope innovations have revolutionized satellite communication. Even the humble Wi-Fi router owes a debt to astronomers tweaking receivers to catch faint interstellar signals. The tools we build to listen to the universe often end up transforming life on Earth in ways we never anticipated. Perhaps most profoundly, the search reframes our relationship with time. A signal reaching us today might have been sent when dinosaurs roamed Earth, or from a civilization that flared out millennia ago. Conversely, any message we transmit could outlast humanity itself, etched into the void long after our cities have crumbled. This interstellar long game teaches patience and humility. We're not just passive listeners, but active participants in a cosmic dialogue that may span epochs. So where does that leave us? However this chapter ends with discovery or enduring silence, the act of searching has already altered our trajectory. It's expanded our definition of life, sharpened our tools, and reminded us that curiosity is humanity's most enduring legacy. The next time you glance at the night sky, remember, you're part of the first generation with the technology to potentially hear back. And whether the cosmos answers or not, the question itself, are we alone, will keep propelling us forward, one frequency at a time. Keep listening, stay wonderstruck. Because the universe's greatest story might still be waiting to crackle through the static. The cosmic whisper beckons, a siren call woven into the static between stars. These enigmatic signals, whether the haunting silence of the Fermi paradox or the electrifying blip of the wow signal, aren't just scientific curiosities. They're fragments of a grander story, one where humanity plays the dual role of both seeker and subject. Every unexplained pulse, every flicker of distant light, is a breadcrumb trail leading us deeper into the labyrinth of cosmic possibility. And while definitive proof of interstellar neighbors remains just out of reach, the search itself has reshaped us. We've built telescopes that listen to the heartbeat of neutron stars, trained AI to decode patterns in noise, and even dared to broadcast our own fragile hello into the void. But here's the beautiful paradox. The longer the silence stretches, the louder it speaks. Each dead end forces us to refine our tools, to question our assumptions, and to confront the humility of our place in the universe. Maybe the answers won't come as a crisp radio transmission or an alien megastructure, but as a slow dawning, a realization that the cosmos communicates in ways we're only beginning to fathom. Gravitational waves, quantum entanglement, or even the subtle chemistry of exoplanet atmospheres might one day carry the message we've longed to hear. Or perhaps the greatest revelation will be this, that in a universe so vast, the act of listening is its own form of connection. So keep your eyes on the sky and your ears tuned to the static. The next great discovery might arrive as a burst of data on a scientist's screen, or as a fleeting anomaly noticed by an amateur stargazer halfway across the world. And when it comes, whether tomorrow or a century from now, It won't just answer the question of whether we're alone. It will remind us that curiosity is the thread stitching humanity into the cosmos's grand tapestry. Until then, the stars remain both our question and our invitation. Thanks for joining this journey through the whispers of the void. If you felt that same spark of wonder, hit like, subscribe, and drop your thoughts in the comments below. After all, the conversation about our place in the universe doesn't end here. It's only just begun.